guys, welcome to this video, and in this video we are going to talk about the kinetic molecular theory of gases and its relationship to the ideal gas law. Alright, first and foremost we're going to conduct a brief review, and I call this our ground zero. Alright, so a gas is a collection of particles that are in constant, rapid, random motion. Sometimes we refer to this kind of motion as Brownian motion. Alright, so the particles in a gas are always colliding with one another, and they are bumping towards the wall of the container. Hence, we can guarantee that there is random motion because once they bump or collide with one another, it changes its direction, and this collisions happens very often. Alright, million times per second. That's why we cannot predict them. Right, that's why we use the word random for that scenario. Alright, next is a gas will always fill its container because of the second law of thermodynamics, because there is an increase in its entropy. And then the effects of intermolecular forces are generally small and negligible, so we can neglect them when we are doing calculations. So due to this, we have the chance to formulate the ideal gas law for approximating the behavior of our gases at room temperature. Alright, so next is we can use four variables to describe the behavior of the gas. One is its pressure, which is we use P, lowercase p, and then we have temperature, which will be in Kelvin scale. Alright, and then we have the volume. We have V for the volume, and N, lowercase n, for the number of moles present in the system. Alright, so some laws are formulated to describe the behavior of the gas, which was done in the past. We have Boyle's law, which was formulated by Robert Boyle in 1642. This states that as the pressure increases, the volume of the gas decreases. Alright, so this is true when temperature is held constant. So we have the Charles law, which was formulated by Jacques Charles in 1787. He is a known balloonist, and this states that the temperature of the gas increases, the volume also increases, provided that pressure is held constant. Next is we have the Dalton's law of partial pressure, which states that the pressure exerted by the mixture of gases is equivalent to the sum of its partial pressure, and this was formulated by John Dalton in 1801. Next, we have the Avogadro's law, which states that at the same condition of temperature and pressure, equal volumes of different gases will contain equal amounts of number of molecules. This was formulated by Amedeo Avogadro in 1856. Next, we have the Gay-Lussac's law, which states that the temperature of an enclosed gas increases. So if it increases, the pressure will also increase, provided that we held the volume constant. And next, we have the combined gas law, which states that the ratio between the product of pressure and volume to the absolute temperature of an ideal gas is constant. Next, we have the Graham's law of effusion and diffusion, which states that the rate of effusion and diffusion of gases are proportional or inversely proportional to the square root of its molecular mass. So this was formulated by Thomas Graham. He is a Scottish chemist, which I think he has done this work in the time frame of 1805 to 1869. So you can read it on some other resources. Alright, so we have the ideal gas law, which will be the topic of this discussion, which predicts the behavior of the gas using the equation of the state. And here is the summary of what we have just reviewed. We have the Boyle's law and its formula, and Charles' law, Gay-Lussac's law, combined gas law, Avogadro's law, ideal gas law, Dalton's law, Graham's law. Alright, so we move on to the development of the ideal gas law and the kinetic molecular theory. So gases do not behave like ideal gas because of its volume, and they occur um, diatomically. Alright, so and it's true that there are intermolecular forces. However, it is possible under certain conditions that real gases behave like ideal gases. All right. So for this to happen, we assume the following things next. So we can assume that we have an ideal gas, and there is a specific container, and it has a defined volume V. All right, and this volume has an amount of infinitely many number of molecules of ideal gas. So all of these gases acts like point particles. That is, they do not have volume, and are very far from one another, and are not affected by intermolecular forces. And next thing is they are in constant random motion, as I have said, just like the gases, and they are bumping towards one another, and they are bumping towards the wall of the container, and they follow Newton's law of motion. And next we must have an ideal wall or boundary that do not absorb the momentum of the ideal gas during collisions. That means all collisions are elastic. Alright, so we can derive the ideal gas law and KMT, and we can use the following facts about the situation. We have V for the volume of the container, we have N for the number of molecules, and P for the momentum of the gas molecules. And we know that according to Newton, that is equivalent to mass times its velocity. Alright, so we can use the diagram right here. We have a yellow cube, alright, and we have a cylinder inside it. So we are going to focus on the cylinder to calculate something. Alright, so the number of particles that hits the wall of the container is equal to the number of particles per unit volume having velocity Vx. Alright, so meaning to say there is a concentration of particles per unit volume, and the only particles that will hit our part here, cylinder, or yeah, will be the particles that are present here at the other end of the container at the time interval dt. Alright, so the total number of particles that has the chance to collide the base of the cylinder right here is equivalent to the area of the circular base times the length of the cylinder times the amount of the particles per unit volume. Alright, so the formula given to it is equivalent to N all over V times the area, or the area of the base, which is circular, times the velocity of the particles, Vx, alright, times dt. So because Vx times dt gives you the distance traveled, which is actually the length of the our cylinder. Alright, next thing is to count the number of collisions happening per unit change in time. Alright, so assuming that all of the particles hits it, the average we get it using arithmetic or using statistics. We just have to use 1/2. So we have to multiply this by 1/2. So that's gonna be 1/2 times N all over B times A times Bx times dt. Alright, next thing is to find the change in momentum per unit particle. So we actually get one particle that is at this point in time bouncing towards or traveling towards the wall. Alright, so this gas particle has momentum. Alright, P is equivalent to negative mvx because it is towards the negative x-axis, and it will hit the container, and then the container will kick it off. Alright, so there is a change in momentum, and P2 is equivalent to mv2. Alright, so the total change in momentum is given by delta P. According to our formula, delta P is equivalent to P sub 2 minus P sub 1, or the final momentum minus the initial momentum. Alright, so we can do some substitution, and the momentum change per particle is given by delta P is equivalent to P2 minus P1, which is equivalent to mv sub 2 in the negative in the x-axis, which is positive, and then minus negative mv1. Alright, so once we execute this, negative minus negative will become positive. Since they are the same, we have delta P is equivalent to positive 2 mvx. Alright, now we can actually find the total momentum change of the system by multiplying the change in momentum per particle times the total number of collisions happening. Alright, so this is the momentum per particle, and we're just gonna to multiply it to the number of particles that are colliding to the walls of the container, and half of this particle hits the wall and half of them leaves the wall. Alright, so we can actually simplify this formula, and you will see that the denominator will cancel out. So 1/2 here times 2 here will be cancelled out. So the total momentum change in the system is equivalent to dpx. Alright, so those of you who know a little bit of calculus will actually see that this is a little bit of calculus. dpx is the change in momentum in the x-axis, is equivalent to n all over b times a times mvx squared times dt. Alright, now we can use Newton's law of motion. Alright, so this is the momentum, and because the change in momentum means that there is a change in velocity. Alright, because you will see that there will be a change in direction, and according to the first law of motion, no one can change the direction of motion unless acted upon by an unbalanced force. So there is a force involved in the change in the direction. So there is force involved, and this can be attributed to the change in velocity. Alright, so we can actually rewrite second law in terms of the momentum, and that's here. So sum of all the forces is equivalent to m times the quantity of b sub 2 minus b sub 1 is equivalent to ma, and that's gonna be in terms of momentum m times derivative of b with respect to time. So that is equivalent to derivative of the momentum with respect to time. So we can solve for the force, and the sum of all the forces is equivalent to the derivative of the momentum in the x-axis divided by time. Alright, so dpx over dt is equivalent to n all over v times a times this one mvx squared, and that is equivalent to n times quantity n times a times mvx to the power of 2 all over v. So you will see that we just divided by dt. Alright, so solving for the pressure, so we have the force, right? So, and we define pressure as force per unit area. So we divide the equation by A. So the pressure is equivalent to sum of all the forces all over A is equivalent to dpx divided by A dt. Alright, so we divide both sides by A, and you will see that A will cancel out, and the resulting formula is equivalent to n times mvx to the power of 2 all over b. Alright, so next is solving for the pressure in a given volume, because we just have solved the pressure exerted on one wall of the container, but we have to solve for the other two axes, which is the x and y axis. So we're going to solve for pressures exerted in the 3 dimensions px, py, and pz. Alright, so suppose that we are going to reverse or twist the cube. All right. So the quantity of gas stays the same, the velocity of gas stays the same. So it's just that there is a change in orientation, but we can say that px is equivalent to py is equivalent to pz. All right. So each wall of the container receives equal amount of forces or of pressure. So we can actually get the average pressure, and that is felt by the container using some arithmetic. Right, so using some statistics, so we can rewrite the average pressure. P average is equivalent to the sum of the pressures all over 3. All right, which is equivalent to px plus py plus p sub c all over 3. All right, so we can just factor out n times m times the quantity bx plus by squared plus bc squared all over 3 all over times b. All right, so and we will find out that we just change the orientation, but the velocity of the particles does not change, and it's always equal to bx here is equivalent to by and is equivalent to bc. All right, so we can actually use to add them and divide it by 3, and we will see that the resulting equation is equivalent to p average is equivalent to 1/3 n times mass of its particle times the average velocity squared all over v. All right, so that is the pressure that is felt inside the container. All right, or felt by the walls of the container. And now we can actually relate this pressure to the kinetic energy of the gas. All right, so we'll just do a little bit of factoring, and when you do the factoring, you will notice that we have mv squared as a factor. All right, and once we insert 1/2 in that equation, it will be equivalent to the translational kinetic energy. So we try to rewrite the right hand side of the equation in terms of KTR by substituting 1/2 mv squared and doing some arithmetic, and you will see that P average, which is equal to 1/3 n times m times b squared all over b, will become P average is equivalent to 1/3, all right, or 2/3 and v times the quantity of 1/2 mv squared. All right, so you will see that we insert 2 here and 3 here, so to make the equation balance. All right, so and we mentioned that 1/2 mv squared is KTR, so we write 2/3 KTR all over v. All right, so KTR here is the translational kinetic energy. All right, so we can write, so once we got cross multiply b to the other side, we have pressure and volume, or PB, is equivalent to 2/3 KTR. So this means that the change in the translational kinetic energy of the gas gives rise to the increase in both pressure and volume, because this means that there's more energy here, so the gases will have the more kinetic energy to move, so it will have more energy to push the boundary, so there will be more pressure, and if it does, if the boundary gives into the pressure, it will explode or expand. Alright, so that's the meaning of it. So meaning to say, if we increase the energy, there will be increase in pressure and temperature. So this equation will be related to the ideal gas law, or the ideal gas law will be related to the kinetic molecular theory if and only if this equation PB is equal to 2/3 KTR will be equal to PB and RT in such a way that KTR is equivalent to 3/2 nRT. Alright, so you will see that we just substitute things. Alright, since n is the number of moles and this is constant, and R is also constant. Increase in KTR due to the increase in is due to the increase in temperature. All right, so meaning to say that when the temperature of the gas increases, it will change KTR, and then it will in turn change pressure and volume. So hence the change in temperature changes the pressure and the volume of the gas in a system. All right, so if there is no constraints there, so it will naturally the change in temperature tends to expand things. All right, so that's another lecture in thermodynamics. So we can calculate the average energy per molecule of the gas. So we just have to use the formula KTR is equivalent to N times 1 half mv squared, and just divide it by the total number of molecules in the system. Alright, so KTR all over N is equivalent to 3 over 2 nRT all over N. So we can regroup. Okay, we have 3 over 2 times N small n divided by big N times RT. Alright, R there is a constant. Alright, and T is the temperature in Kelvin. So we want to find the total number of molecules in, and that is equivalent to the number of moles N times the Avogadro's number. Alright, so we have the formula N, so which is the number of molecules, alright, is equivalent to N, which is the number of moles, times N sub A, which is the Avogadro's number. Alright, so KTR per molecule, alright, is equivalent to this formula, 3 over 2 times N all over N times big N sub A is equivalent to RT. Alright, so you will see that we can cancel out N all over N, and what will remain is the Avogadro's number, and the new formula is equivalent to 3 over 2 R, which is universal gas constant, divided by the Avogadro's number times time. And R all over N sub A is frequently occurring in chemistry and in kinetic molecular theory, and this is called the Boltzmann constant. Alright, so we have N all over N sub A, or R all over N sub A is equivalent to K, which is the Boltzmann constant, and we can solve for the value of the Boltzmann constant right here. We have 8.314 joules per mole per Kelvin, divided by the Avogadro's number, and you're gonna get 1.38 times 10 to the negative 23 joule mole per Kelvin times molecules. Alright, so that's the value for the Boltzmann constant. So we can rewrite the formula for the KTR as 3 over 2 KT. Alright, so there we go. And since we know the Boltzmann constant, we can rewrite the equation as I've told you, and we can use this one. KTR is equivalent to 3 over 2 R all over Avogadro's number times the temperature, and this is equivalent to 3 over 2 K, which is the Boltzmann constant times the temperature. Alright, so this is the formula for calculating the average energy per molecule of the gas. So hence, the energy per molecule of the gas, 3/2 of the product of the Boltzmann constant and the absolute temperature. Alright, so it does not depend on the type of gas. Alright, so which is more energetic and which is not. So it just depends on the absolute temperature. Alright, so we can actually find the average energy per mole of the gas. We just have to multiply both sides by the Avogadro's number. Alright, and we can get KTR per mole is equivalent to 3 over 2 R times the temperature. Alright, so we can rewrite this using the relationship R all over n sub A is equivalent to K. And hence R is equivalent to n sub A times K. Alright, so we can rewrite this formula. And you will see that we can say the energy of 1 mole of gas doesn't depend on the type of gas, but on the measure of its absolute temperature. So practice problems. Alright, so as always, I am telling everyone that practice makes you perform better. So there is a deep underthings to the 0.24 times 10 to the 6 liters of methane gas or CH4. At it has a pressure of 1.5 times 10 to the power of 3 kilopascals, and it has a temperature of 42 degrees Celsius. So how many moles of methane or CH4 does the cavern contain? So for miners, alright, so for geologists, for researchers, for so this is very functional for you guys. So we have to analyze that and it is stated that we need to find the number of moles of CH4. Alright, so I have here the table. So this is the required mole CH4, and we have the given and the volume, which is 2.24 times 10 to the 6 liters, and we have the pressure, which is 1.5 times 10 to the power of 3 kilopascals, and we have the temperature, which is 42 degrees Celsius, and we have to convert that to Kelvin. We have to add 273.15, so we have 315.15 Kelvin, and we have the value of R. So we can actually choose a value of R that fits according to the units. Alright, so we have to use the formula. PB is equivalent to nRT, and since we are looking for the mole, we are going to solve for the N, and that's gonna be N is equivalent to PB all over RT. So once we plug in the values, here it is, you're gonna find the N is equivalent to 1295054 mole of CH4. Alright guys, so I hope you learned something out of this short video about the ideal gas theory, alright, and its relationship to the ideal gas law. KMT and ideal gas law. If you have any other comments, suggestions, or any questions about the problem or about our topic, you can comment down below. And if you like this video, please give us a thumbs up, and don't forget to click the subscribe button and hit the notification bell. Alright, subscribe button, notification bell to get updated whenever we post new videos like this. So bye bye guys, see you once again in the university.